Here is the edited English version with all numbers written out in words. On June 24, 2021, at 1:22 in the morning, in the resort town of Surfside, Florida, the 12-story Champlain Towers South condominium folded into the ground in just 12 seconds. 98 people died in their sleep. The building had stood for only 40 years. Now imagine a very different picture. In Pittsburgh, Pennsylvania, bridges built back in the 1920s still carry thousands of cars every single day. The Empire State Building skyscraper, raised in 1931 using steel from Bethlehem steel, has already stood for almost 100 years, and no serious engineer doubts that it will remain solid for another century. What is the difference? The answer lies deep under the concrete, inside the reinforcing steel bars. And that answer may surprise you. The steel your great-grandparents' generation produced and the steel poured today are, in practice, two completely different materials, even though on paper they carry the same name. This is the story of how America lost the craft of making true structural steel, of how cost-cutting turned into catastrophe, and of the hidden price all of us pay for recycled metal. In 2025, the American Society of Civil Engineers published another report card for United States infrastructure. Bridges received a grade of C, simply average. But behind that modest letter hides a frightening set of numbers. Out of 621,218 bridges in America, almost half, 49.1%, are rated only fair. Another 6.8% are classified as poor. The average age of an American bridge is 47 years, and the average design life the engineers planned for was 50 years. In other words, almost every second bridge in the country is nearing the end of its intended lifespan. And yet there is an obvious question. If the typical design life is 50 years, why are bridges from the 1920s and 1930s still standing and working? The George Washington Bridge, the Golden Gate Bridge, the Brooklyn Bridge, they are all more than 90 years old, and they carry loads their builders could not have imagined. The explanation lies in a process once known as open-hearth steelmaking, and in what eventually replaced it, the electric arc melting of scrap. According to NACE International, the direct annual cost of corrosion in the United States reaches $276 billion. That is about $1,400 for every American. Roughly 3.1% of the country's gross domestic product, more than the entire federal education budget. And a huge share of those losses comes from corrosion of reinforcing bars inside reinforced concrete structures. A typical bridge deck in America lasts, on average, 30 years. Not 100, not 75, 30 years. After that, it must either undergo major rehabilitation or be replaced entirely. Why? To understand that, we need to go back in time. Back to an era when steel was smelted slowly, carefully, and with deep respect for the material. The golden age of American metallurgy. Pittsburgh, 1886. A permanent curtain of smoke hangs over the city, so dense that street lamps burn even at midday. Workers call it Pittsburgh fog. Inside this smoky inferno, a new America is being born. At the Homestead Works plant of Carnegie Steel, engineer Julian Kennedy starts up the first large-scale open-hearth furnace in the country. This technology, invented by the German engineer Carl Wilhelm Siemens and refined by the French brothers Pierre and Émile Martin in 1865, will permanently change the face of American industry. The principle of the open-hearth furnace sounds deceptively simple. A huge, shallow basin lined with fire brick holds up to 600 tons of molten metal. A gas flame preheated in regenerative chambers to more than 1,600 degrees Celsius licks the surface of the liquid steel for hours at a time. The secret lies in those hours. The heat cycle lasts anywhere from 8 to 12 hours. By comparison, a modern electric arc furnace can melt down a batch in 30 to 50 minutes. But this slowness is not a flaw. It is an advantage. The plant chemist, Charles Schwab, the man who would later become president of Bethlehem Steel, takes samples from the melt every hour. He measures the content of carbon, sulfur, and phosphorus. Then he gives the steelworkers precise instructions. Add more limestone to bind sulfur. Sprinkle in iron ore so that more carbon will burn out. Let it cook for another hour. The smell on the casting floor is a raw mix of burnt iron, lime, and sweat. The temperature near the furnace climbs above 50 degrees Celsius. Men work in shifts barely 20 minutes long, then step back into the cooler air to catch their breath. But when the steel finally pours into the ingot molds, it is as close to perfect as human skill can make it. Nitrogen content, 30 to 50 parts per million. Sulfur, less than 0.04%. Phosphorus, controlled down to hundredths of a percent. That level of purity is only possible when you have the one thing modern production lines hate most: time. Time for impurities to float to the surface and drift into the slag. Time for chemical reactions to run to completion. Andrew Carnegie, the owner of the empire, liked to say, "Watch the cents and the dollars will take care of themselves." But on steel quality, he refused to cut corners. He understood that bad steel would always cost more in the end. By 1900, the open-hearth process had pushed the Bessemer method almost entirely out of structural steel production. America was producing more than 10 million tons of steel per year. By 1910, annual output had climbed to roughly 24 million tons, and that steel was literally building the country. Bethlehem, Pennsylvania, the 1920s. The 5-mile-long complex of Bethlehem steel plants stretches along the Lehigh River. 31,000 workers in 3 shifts produce the material from which modern America is being assembled. The company's chief engineer once said a line that became legend: "Bethlehem Steel owns New York." It was not much of an exaggeration. In March 1930, work begins in Manhattan on the Empire State Building. Bethlehem Steel supplies 57,000 tons of steel, and does it in record time. Every day, a train loaded with finished beams rolls onto the construction site. Each beam is marked. Each knows its exact place in the frame. Bethlehem Steel gives birth to what the industry calls the gray beam. These eye-shaped sections, rolled using the company's proprietary technology, have near-perfect geometry and a uniform internal structure. They are lighter than comparable European beams while delivering the same strength. But the real key is the chemistry of the metal itself. Open-hearth structural steel contains roughly 0.15 to 0.25% carbon. That is enough for strength, but not enough to make the metal brittle. Manganese, added in a carefully controlled amount, increases toughness. Silicon improves weldability. Above all, harmful impurities are held to a minimum. Copper, less than 0.05%. Tin, only trace amounts. Nitrogen, carefully controlled. These figures may sound abstract. In reality, they decide the fate of entire buildings. Copper in steel causes a problem metallurgists call hot shortness. At rolling temperatures, around 1,100 degrees Celsius, copper forms a liquid phase along the grain boundaries. The metal begins to crack under its own weight. If the copper content climbs above about 0.1%, trouble is almost guaranteed. Tin is even more treacherous. Even around 0.04%, tin greatly intensifies hot shortness. In an open-hearth furnace, these elements are controlled from the very start. The charge, the carefully chosen mix of pig iron, scrap, and ore, is selected with precision. The scrap is mostly internal, offcuts from the plant's own production with known and consistent composition. Not shredded cars full of copper wiring, not discarded appliances filled with tin-based solder. The Golden Gate Bridge in San Francisco received its steel from 5 different Bethlehem steel mills. 83,000 tons of metal traveled by rail to Philadelphia, and from there by ship through the Panama Canal. The bridge opened in 1937. It still stands today, 88 years later. The George Washington Bridge over the Hudson River, built entirely from Bethlehem steel, now carries more than 100 million TEUs, vehicles every year. It is 94 years old. These structures were originally designed for a service life of about 50 years. They have already lasted twice that long, and they show no intention of quietly retiring. Darlington, South Carolina, in 1969. On the edge of a small town, between pine forests, a plant goes into operation that will change the American steel industry forever. It is built by the Nuclear Corporation of America. Yes, you heard that right, a nuclear company. But at this point, the company has long had nothing to do with atomic energy. The president of the firm is the 44-year-old metallurgist F. Kenneth Iverson. He joined the company in 1962 to run the Volcraft division, which produced steel beams. Very quickly, he realizes something. Dependence on the big steel makers is crushing the business. Prices rise, quality fluctuates, imports are unreliable. Iverson makes a decision. He wants to produce his own steel. But not like the giants United States Steel or Bethlehem Steel. Not in enormous Siemens Martin open-hearth furnaces that demand investments in the billions. Iverson chooses a different path. Electric arc furnace technology. The principle sounds simple and elegant. 3 graphite electrodes are lowered into a vessel filled with scrap steel. The electric arc, basically a controlled lightning bolt, heats the metal to melting temperature. After about 1 hour, a batch of liquid steel is ready. Nucor's first plant, that is what the company will be called starting in 1972, costs around $6 million. About 1/10 of what a classic integrated steel corporation would consume. And this plant works. By 1972, Nucor is listed on the stock exchange. By 1975, the company makes it into the Fortune 500 list. Iverson becomes a legend in the American business world. His book, Plain Talk, is still analyzed decades later at Harvard Business School as an example of unconventional thinking. The mini-mill model spreads across the entire country. The old giants, weighed down by pension obligations, powerful unions, and outdated facilities, cannot keep up. One after another closes its gates. Bethlehem Steel has not existed since 2003. The last operating Siemens Martin open-hearth furnaces in the United States go dark as early as 1992. The electric arc furnaces have won. Today, Nucor is the largest steel producer in America. 24 electric arc furnaces are distributed across the United States. Installed capacity is around 29 million tons of steel per year. The company recycles more than 18 million tons of scrap annually and proudly, and rightly, calls itself the largest recycler of secondary metals in North America. But behind this success, a problem is hiding. Scrap is not pig iron. Imagine a car that has lived out its time. For 20 years it has driven on American roads. Now it sits in a scrapyard in Texas and waits for its second death. A power hammer weighing about 40 tons slams into the body. Once. Again. A third time. The vehicle becomes a flat, twisted metal slab. Then it goes into the shredder. A gigantic metal meat grinder tears the car into pieces about the size of a fist. A magnetic separator pulls out iron and steel. The rest seems to end up as waste on the heap. But this rest does not disappear completely. Every car contains kilometers of copper wiring, electric motors for power windows, radiators with copper tubes, brass clamps at the battery, solder joints with tin on the circuit boards of onboard electronics. Even after careful sorting, part of these metals remains in the steel scrap. When this scrap goes into the electric arc furnace, a chemical reaction happens. More precisely, it does not happen the way metallurgists would want it to. Copper and tin are thermodynamically more stable than iron at steel's melting temperatures. They barely oxidize. They do not transfer into the slag. They do not evaporate. They stay in the molten metal forever. Metallurgists call these companions tramp elements, roaming or interfering elements, often also residual elements. In every case, they are impurities that can practically no longer be removed with standard refining methods. A study published in 2017 in the journal Environmental Science and Technology shows the scale of the problem. The copper content in recycled steel rises slowly but steadily with each recycling step. In the 1950s, the average copper share in steel scrap was about 0.1%. In the 2010s, it reached values of roughly 0.2 to 0.3% in some scrap categories. And that is only the beginning. Experts predict that after 2040, the volume of high copper scrap will exceed demand for products that can tolerate steel that contaminated. In other words, there will be more scrap than there is capacity to turn it into high-quality steel. What happens when copper gets into steel? When heated to hot rolling temperature, roughly 1,100 to 1,200 degrees Celsius, the iron at the surface oxidizes. Scale forms. But copper does not oxidize to the same extent. It collects beneath that scale, at the boundary between metal and oxide layer. Once the copper content exceeds roughly 0.1%, a thin, liquid copper phase forms. Copper's melting temperature is about 1,085 degrees Celsius, clearly below rolling temperature. This liquid copper layer creeps along grain boundaries into the interior of the metal. The grains lose cohesion, and when the rolling mill applies pressure to the slabs, they begin to tear. This phenomenon is called hot shortness. The cracks are not necessarily visible to the naked eye. Often they are only microscopic fissures, but they are there, and they mark weak points in the internal structure of the steel. Tin makes the problem even worse. As little as about 0.04% tin, around 40 grams per ton of steel, drastically increases hot shortness. Tin lowers the melting temperature of the copper-rich phase even further and makes it easier for it to penetrate along grain boundaries. A Japanese study from 2011 showed steel with about 0.3% copper and roughly 0.02% tin loses ductility during hot forming in a critical way. The metal refuses to bend, it breaks. But there is yet another element that almost nobody outside metallurgical laboratories talks about. It is invisible, odorless, and colorless, and its influence on steel properties is enormous. Nitrogen. In classic Siemens Martin steel quality, the nitrogen content was typically around 30 to 50 parts per million. In electric arc furnace steel, it is more in the range of 70 to 120 parts per million. The difference is roughly 2 to 3 times. Why? The answer lies in the nature of the process itself. The electric arc in the furnace reaches temperatures of up to about 5,000 degrees Celsius. That is roughly the temperature of the sun's surface. Under such conditions, the nitrogen molecules in the air break apart into individual atoms. Atomic nitrogen dissolves immediately into the liquid steel melt. In the Siemens-Martin furnace, flame temperature is lower. The melt is heated more slowly and sits under a protective slag layer. The metal's contact with the atmosphere is far smaller. Nitrogen simply does not get the chance to accumulate in comparable amounts. What does nitrogen do to steel? It triggers a phenomenon called strain aging. Nitrogen atoms lock dislocations in the iron crystal lattice. The steel becomes harder, but at the same time more brittle. It loses the ability to absorb impact energy without failing. This is especially critical in welded structures. During welding, the temperature in the seam zone reaches melting temperature. Existing nitrides, compounds of nitrogen and metals, break down. Nitrogen is released and spreads into the heat-affected zone around the weld. As it cools, nitrides form again, but this time in other places and in other forms. The result, the heat-affected zone next to the weld becomes brittle. Engineers speak of embrittlement of the heat-affected zone. Under impact loads or at low temperatures, cracks prefer to form exactly here. A study by the Electric Power Research Institute as early as 1992 recognized that nitrogen content in electric arc furnace steel is a critical problem for deep-drawing quality products. Automotive body panels, food cans, complex drawn and stamped parts. All of these applications require steel with a very low nitrogen content. There are technical ways to reduce nitrogen in electric arc furnace steel. You can stir the melt with argon. You can use vacuum degassing. You can add hot pig iron or directly reduced iron to dilute the scrap. But every one of these measures costs additional money and additional time. And that is where the paradox lies. The electric arc furnace displaced the Siemens-Martin furnace mainly because of its speed and low cost. Additional refining steps erase that advantage again. That is why manufacturers, for many applications, especially for reinforcing bar in reinforced concrete structures, simply accept the higher nitrogen content as a given. Reinforced concrete is a brilliant invention. Concrete carries compression extremely well. It can hold the weight of a multi-story building. But under tensile stress, it is weak. Even small strains are enough to make it crack. Steel reinforcement offsets exactly that weakness. The steel bars inside the concrete take the tensile forces. Concrete and steel work together. They form one shared structural system in which the materials complement each other. But inside this perfect duo, there is a serious enemy. Steel rusts. As long as the reinforcement is protected by the strongly alkaline environment of fresh concrete, with a pH value of roughly 13, a very thin, dense iron oxide film forms on the steel surface. This passive layer shields the metal from further corrosion. But concrete is not solid glass. It is a porous structure. It absorbs water like a dry sponge. And with that water, enemies arrive. The first enemy is chlorides, de-icing salt from winter roads, seawater in coastal structures. Chloride ions push through the pores of the concrete and destroy the protective passive layer on the surface of the reinforcement. The second enemy is carbonation. Carbon dioxide from the air reacts with calcium hydroxide in the concrete and forms calcium carbonate. The pH drops. If it falls below roughly 9, the passive layer on the steel becomes unstable and gradually dissolves. When that protection disappears, corrosion begins. And this is exactly where the properties of the steel become life-critical. Steel with high levels of residual and tramp elements, copper, tin, sulfur, tends not to corrode evenly, but locally. So-called pitting forms, small, but deeply cutting pit defects in the surface of the metal. Pitting corrosion is especially dangerous because it concentrates damage into tiny areas instead of spreading it evenly. Nitrogen in the steel also plays a role. Studies show that elevated nitrogen content can accelerate localized corrosion in chloride-rich environments. But the worst part is what happens next. Rust has a much larger volume than the original steel. Depending on which oxides form, this volume can be roughly 2 to 6 times larger. When reinforcement rusts, it expands. The concrete around the bar is put under internal pressure. At first, fine, invisible micro-cracks form. Then, visible crack lines appear on the surface. Finally, pieces of concrete begin to break off. Entire slabs detach. What engineers often call concrete cancer or spalling. Those cracks become entry points for even more moisture and chlorides. Corrosion accelerates. The cycle starts again, and it runs faster and faster. According to the Massachusetts Institute of Technology, a typical bridge deck system in the United States lasts, on average, about 30 years before major rehabilitation or replacement becomes necessary. 30 years for a structure that, by design intent, should survive closer to roughly 75 years. A significant part of this gap has to do with the properties of the reinforcing steels. At 1:14 in the morning on the night of the 24th of June, 2021, surveillance cameras record the first anomalies. The slab of the pool deck beside the 12-story Champlain Towers South condominium in Surfside, Florida, drops down into the parking garage below. 8 minutes later, at 1:22, the central section of the building collapses. 12 stories fall into themselves, floor by floor, in about 12 seconds. Just a few seconds after that, the eastern wing also collapses. 98 people die. The building is about 40 years old. The investigation led by the National Institute of Standards and Technology of the United States, NIST, is not yet complete. The final report is expected no earlier than 2026, but many details are already known. Investigators have conducted more than 1,000 sample analyses and material tests on concrete and rebar pieces from the rubble. They used petrographic analysis under high-resolution microscopes, examined the condition of the cement matrix and the aggregates. What did they find? First, the concrete in the pool deck slab was weaker than the building codes of 1981 required, the year the building was constructed. Second, the columns supporting that slab had lower load capacity than intended for such stresses, and at the center of many findings was corrosion. Professor Don Lehman of the University of Washington said, after reviewing video footage from federal investigators in the debris area, that the corrosion at the base of one of the critical columns had been astronomical, as she told the Miami Herald. She added that damage that severe should have been noticed during the 40-year mandatory inspection that was underway at the time of the collapse. If the corrosion is that strong, it has to be fixed, Lehman emphasized. Research engineer Abiyeyuwa Agayere of Drexel University paused when he saw the concrete in the video recordings. Instead of the usual mix of cement matrix and clearly embedded aggregates, he saw an almost homogeneous, whitish powder structure. "The white color shocks me," Agayere said. "That doesn't look like normal concrete." The most likely cause: decades under the influence of seawater. Champlain Towers South stood only a few dozen meters from the Atlantic. The building's parking garage was regularly flooded with water. Maintenance teams pumped it out. but it returned again and again. Later investigations found that the groundwater level beneath the building had risen due to sea level rise. Saltwater repeatedly made direct contact with the foundation and underground structural components. Chlorides from the seawater penetrated the concrete, destroyed the passive layer on the reinforcement, and set corrosion in motion. A grand jury in Miami-Dade County concluded in its report from December 2021 that there was reasonable certainty that there had been invisible corrosion and a weakening of the concrete in the foundation and the basement columns. The jury also warned that the problem was not limited to this one building. Saltwater could create dangerous conditions for reinforced concrete structures along Florida's entire coastline. Let's talk about money. Rebar is among the cheapest steel products there are. It does not need a flawless surface like automotive sheet. It does not need an ultra-tight chemical analysis window like high-alloy tool steels. The tolerances are wide. The requirements look comparatively modest. That is exactly why today almost all rebar worldwide is produced from recycled scrap in electric arc furnaces. In 2024, the Nucor Corporation processed roughly 18 million tons of scrap. Most of it was so-called obsolete scrap. End-of-life cars, old household appliances, scrapped building structures. This is precisely the scrap category with the highest copper and tin contents. In theory, you could reduce the concentration of these foreign elements by diluting the scrap with primary iron. Direct reduced iron, DRI, typically contains less than 0.01% copper. Pig iron is also comparatively clean. In practice, that means extra cost. Direct reduced iron is roughly 30 to 50% more expensive on the American market than normal mixed scrap. Pig iron requires a blast furnace, and there are only a few left in the United States. Imported pig iron adds logistics and transport costs. So the industry chooses another path. Steel with elevated residual contents is deliberately routed into products where purity requirements are lower. Rebar is almost ideal for that. The ASTM A615 standard, the most important American standard for rebar, allows up to roughly 0.4% copper in the steel. That is about 4 times the threshold at which hot shortness problems would begin for strip and sheet products. So the industry very consciously produces rebar from metals that would not be accepted for higher demand applications. And it works, up to a certain point. Fresh rebar with about 0.3% copper behaves, in the lab, almost identically to steel with only roughly 0.05% copper. Tensile strength, yield strength, basic mechanical properties look the same on the test bench. The difference appears after 20, 30, 40 years in service. A study carried out in Egypt on industrially recycled steels showed copper and tin preferentially accumulate at grain boundaries. There they form brittle phases that clearly reduce impact toughness and ductility. Once corrosion begins, those grain boundaries become weak spots where pitting forms especially quickly. Copper-rich precipitates inside the grains act like tiny stress concentrators. Under cyclic loading, and bridges and buildings experience load cycles every day from traffic, wind, and temperature changes. These points become seeds for fatigue cracks. The steel of your great-grandparents did not have these problems in this form. Not because the engineers of the 1920s were smarter, but because their process barely allowed such impurities in the first place. The Siemens Martin open-hearth furnace worked with pig iron as the main feedstock. Scrap was added only in limited amounts, usually from the plant's own production returns with known origin. The long melt time of about 8 hours gave the system time for extensive refining. We traded that quality for speed and low cost. and now we are paying the price. This number appears in every ASCE report on American infrastructure: 178 million. That is how many times Americans cross bridges each day that are classified as structurally deficient, structures in poor condition that urgently need repair. Let's look at the numbers more closely. As of 2023, the United States has 621,218 bridges. About 6.8% of them, roughly 42,000, are in poor condition. Another 49.1%, more than 305,000, are only in fair condition, meaning one step away from deficiency. The average age of an American bridge is 47 years. The average planned service life is about 50 years. Since 2007, new bridges have been designed for a service life of 75 years. But most existing structures come from an older world of standards. AS calculated, to bring all bridges in the country into a safe condition would require, over 10 years, about $538 billion. Actual funding covers only part of that. At the current rehabilitation rate, about 4,900 bridges per year, full renewal would take about 126 years. Bridges built today are supposed to last until around the year 2150, but they will not with the reinforcement we currently use. One example makes the problem clear. Engineers at the Massachusetts Institute of Technology and the company Allium Engineering studied the corrosion problem of reinforcement in bridge decks. Their result: a typical bridge deck system with conventional rebar lasts, on average, only about 30 years before major repair is required. 30 years. Not 75, not 50. 30. The company developed a method in which the rebar is coated with a thin layer of stainless steel. According to their calculations, this would at least triple the service life of such structures. The cost? Only a moderate premium compared to conventional rebar. But the construction industry is slow. Designers reach for what they know. Contractors buy what is cheapest. Owners focus on upfront costs, not life cycle costs. So bridges continue to be built that will rust from the inside in 30 years. In the state of Rhode Island, 22% of bridges are in poor condition, the worst value in the entire country. In Nevada, it is only about 1%. The difference is not an accident. Nevada invests more consistently in preventive maintenance, but even Nevada builds with the same reinforcement as Rhode Island: electric arc furnace steel from recycled scrap, laced with copper, tin, and nitrogen we already talked about. So the question is not whether these bridges will fail. The question is when. There is a certain symbolism in the fact that the ruins of the Bethlehem steel plant in Pennsylvania are now a tourist attraction. 5 huge blast furnaces rust under open sky. Once, they melted pig iron for the greatest structures in America. Today, they are the backdrop for concerts and festivals in the Steel Stacks Cultural Complex. The last worker left the plant in 1995. The company filed for bankruptcy in 2003. But the steel produced here still carries the load of bridges and skyscrapers across the country. Ken Kobus, a third-generation steelworker, worked for more than 40 years in the plants of Jones and Laughlin, LTV, and United States Steel. Both grandfathers were steelworkers. His father was a first assistant at a Siemens Martin open-hearth furnace. In an interview for the project, What It Means to Be American, Kobus remembers, "The hardest work I ever did was as a third assistant at the electric arc furnace. Hand charging, the hottest hell you can imagine. Your clothes were soaked. Sweat ran into your boots. You literally stood in your own broth." But when he speaks about the old Siemens Martin furnaces, his tone changes. When you pour molten pig iron through the open doors into the furnace, it's like the 4th of July. Thousands of sparks shoot into the air, an incredible sight. Maybe there are 40 tons of boiling iron in the ladle and 300 tons in the furnace. He describes how plant chemists took samples hourly, ran analyses, and precisely adjusted the process. How they could stop the melt immediately as soon as the carbon content reached the ideal point. Carnegie often introduced what looked like small changes in the workflow, like always having a chemist on the casting floor. Today, you'd barely mention details like that in management reports. But exactly those little things strengthened the connection between the 3 basic pillars of steelmaking. It was a culture of quality, not in words, but in actions. When Andrew Carnegie had the Edgar Thomson Works built in 1875, he brought the best engineers from the competing Cambria Iron Works. Captain William Jones became superintendent and introduced innovations that made the plant the most productive in the world. But productivity never came at the expense of quality. Carnegie paid bonuses for low scrap rates. He knew cheap, bad steel only leads to an expensive, bad reputation. Bethlehem Steel adopted that philosophy. Charles Schwab, who led the company starting in 1904, declared, "I intend to make Bethlehem the best steelworks of its class, not only in the United States, but in the whole world." And he did. The wide-flange Bethlehem beam shape was a revolutionary product that allowed skyscrapers to be built with less steel. The gray beam became synonymous with reliability and precision. Today, there is not a single plant left in America that produces steel by the Siemens Martin process. The last furnaces went out in 1992. Worldwide, only a few remain in operation, in Ukraine, in India, and in Russia. An era ended. But its legacy lives on in every bridge pier and in every skyscraper built before the 70s. In Rome stands a building that is almost 2,000 years old. The Pantheon, the temple of all gods, was built under Emperor Hadrian around the year 126 after Christ. Its dome, with a diameter of 43 meters, is still the largest unreinforced concrete dome in the world. Roman concrete is fundamentally different from modern concrete. The Romans used volcanic ash, pozzolana, instead of Portland cement, lime instead of modern binders, and different aggregates for different structural parts, heavier below, lighter above. But the most important thing, there is no reinforcement. Unreinforced concrete works only in compression. The Pantheon's dome is shaped so that all forces inside it are compressive forces. No tension, no steel, no steel, no corrosion, no corrosion, no decay. After almost 2,000 years, the Pantheon still stands in remarkable condition. Compare that to a typical American parking garage from the 1980s. Reinforced concrete slabs, armed with steel bars, open to rain and snow, salted in winter. After 30 years, you see cracks, spalling concrete, rust-brown stains on the surface. After 40 years, major rehabilitation or demolition becomes unavoidable. An author on the platform, The Conversation, wrote about the problems of reinforced concrete. Concrete by itself is an extraordinarily durable building material. The Pantheon in Rome, the largest unreinforced concrete dome in the world, is in remarkable condition after nearly 1,900 years. And yet many concrete structures of the last century, bridges, highways, buildings, are already deteriorating today. The decisive difference is the steel reinforcement inside. The researcher calls for new thinking. We should not treat concrete and steel as inert and unchanging, but as active reacting materials. Moisture penetrates through thousands of micro cracks. One end of a rebar becomes the anode, the other the cathode. An electrochemical cell forms, essentially a battery. And this battery feeds the slow process that turns iron into rust. Rust expands the steel to up to 4 times its original volume. The concrete bursts from within. The process engineers call concrete cancer or spalling is irreversible. There are methods that can slow this process. Cathodic protection, where the structure is electrically biased, or chemical inhibitors that passivate the steel. Newer variants even use bamboo extracts or biological molecules to delay rust. But none of these solutions removes the basic problem. Steel in concrete will rust sooner or later. It is only a question of time, not if. In March 2024, the Harkers Island Bridge in North Carolina was opened. It is considered the longest bridge in the world, built completely without steel reinforcement. Instead of steel, reinforcement bars made of GFRP were used. Glass fiber reinforced polymer. Glass fibers impregnated with a polymer resin matrix. This composite does not rust. Not at all. Chlorides, seawater, road salt, all of it bounces off. It does not conduct electricity, so electrochemical corrosion cannot form. Its tensile strength is higher than steel at the same mass. At the same time, it weighs about 1/4 of comparable steel bars. That makes transport, handling, and installation on site significantly easier. Of course, the material has weaknesses. GFRP has a lower elastic modulus. It deflects more under load. It behaves more brittlely. It does not plastically deform. It breaks abruptly. And it is more expensive than conventional steel reinforcement. But if you calculate across the full life cycle, including all the repairs that would no longer be necessary, the economic balance shifts noticeably in favor of the glass composite. The company Matinbar, a manufacturer of GFRP rebar, emphasizes that projects on coasts, in salty environments, or in regions with harsh winters can recover the material premium within the first 20 years of operation. Another approach stays with metal, with stainless steels. Stainless steel contains chromium, which forms a dense, stable oxide layer on the surface. This chromium oxide layer protects the steel even when chlorides are present. Stainless rebar can last well over 100 years in highly aggressive environments. The obstacle is price. Stainless steel costs about 5 to 10 times as much as normal carbon steel. This is exactly where a compromise comes in. One Allium Engineering founded by 2 Massachusetts Institute of Technology graduates. They developed a process that coats ordinary rebar with a thin layer of stainless steel. The required equipment can be integrated into existing rolling lines, and the price premium compared to normal rebar remains moderate. Co-founder Stephen Japil puts it this way: instead of investing in a bridge and getting about 30 years of life, that same bridge can last 100 years or longer. By 2025, about 45 tons of this coated rebar had already been installed in projects in California and Florida. Allium plans to expand production and bring the technology directly into steel mills. There is a third path, a return to the origins. Unreinforced concrete, designed rigorously according to the principles of the Pantheon, can remain stable for millennia. Modern numerical methods allow structures to be shaped so that nearly all relevant stresses are compressive stresses. The Swiss architect Philippe Bloch is already building such structures today. His Nest Hilo pavilion in Zurich, an extremely thin concrete shell without any steel reinforcement, shows impressively that this concept works in practice, not just in theory. But the construction industry responds slowly. Engineers design the way they were taught. Construction firms execute what they are used to. Codes and standards change sluggishly, and so most structures in the world will continue to be built with the same material. Steel from electric arc furnaces, made from recycled scrap, threaded with copper, tin, and nitrogen. In metallurgy, there is a term that will shape the future of the entire recycling industry: the thermodynamic trap. The idea is simple and merciless. Every metal has a certain chemical reactivity. Iron is more reactive than copper. That means, during melting, iron preferentially reacts with oxygen and goes into the slag. Copper does not to the same extent. It remains in the melt. With every recycling cycle, copper accumulates further. Imagine a passenger car built around the year 2000. It contains, roughly estimated, about 25 kilograms of copper in wiring harnesses, electric motors, electronics. After 20 years, that vehicle goes into the shredder. Most of the steel flows into new products, but part of the copper goes with it. The new steel finds its way into another car, into rebar, or into a beam. After another 20 to 30 years, that product becomes scrap again. The cycle starts over. With each turn, the average copper concentration in the global steel stock rises another small step. A study published in the journal Environmental Science and Technology modeled this development out to around the year 2100. The results are unsettling. In the business-as-usual scenario, by roughly mid-century, the quantity of scrap with excessively high copper content will exceed demand for products that can tolerate that level of contamination. Put simply, there will be more scrap than can be used sensibly. What do you do with this surplus? One option is export. In many emerging and developing countries, quality requirements for construction steel are still lower. Rebar with relatively high copper content can, in principle, be used for mass housing in parts of Africa or Southeast Asia. But that only shifts the problem into the future and into other regions. It does not solve anything. The second strategy is dilution. Contaminated scrap is mixed with primary iron, direct reduced iron or pig iron, lowering the percentage of foreign elements. Nucor is already moving in this direction. In 2015, the company invested about $750 million in a direct reduced iron plant in Louisiana. There, iron ore is reduced with natural gas, without the detour through a classical blast furnace. But DRI is, in essence, a step back toward a primary process, with all the ecological consequences: mining, carbon dioxide emissions, high energy demand. The third option would be a real technological leap, developing a process that can selectively remove copper from molten steel. On paper, there are several approaches. Copper could be drawn off into molten lead or aluminum, where it dissolves better than in iron. You could try to evaporate copper at extremely high temperatures under vacuum, or you could scale electrochemical refining processes up to industrial size. In practice, none of these methods is economical at industrial scale yet. Not yet. Research groups in multiple countries are working on it. The Japanese New Steelmaking Process Forum has been searching for solutions since the early 1990s. Universities in the United States are testing electrochemical methods. European companies are developing ever more precise sorting techniques for scrap streams. But time is running. One of the authors of the Environmental Science and Technology study summarized it like this: "We cannot recycle steel endlessly without quality suffering. Sooner or later we must decide: accept lower quality steel, find ways to purify it, or rely more heavily again on primary production." A circle closing. We began this story with the catastrophe in Surfside. with 98 people who died in a building that should have stood for decades longer. And we asked, why does the steel of our great-grandparents survive a full century, while modern structures often fail after only 30 years? Now we know the answer, and it is more complicated than we would like. It is not because today's engineers know less than earlier generations. It is not because steel mills deliberately produce bad products. It is neither a conspiracy nor pure negligence. It is a system question. The Siemens Martin open-hearth furnace gave one thing above all: time. About 8 hours of slow refining, in which the plant chemist could take samples, analyze composition, and fine-tune the process. Undesired elements moved into the slag. Nitrogen could barely accumulate. The steel became exceptionally clean. The electric arc furnace gives something else: speed. In about 30 minutes, a heat is ready. Scrap is melted along with its companions. Copper stays. Tin stays. Nitrogen diffuses from the furnace atmosphere into the melt. We traded quality for efficiency, and that trade had good reasons. Electric arc technology uses roughly 3/4 less energy than the classic integrated blast furnace converter route. Carbon dioxide emissions are about 1/3 of the traditional route. Costs are significantly lower. Steel recycling is considered one of the greatest success stories of the circular economy. Millions of tons of metal that would otherwise rot in landfills get a second life. Ore deposits can be conserved longer. Forests do not have to give way to additional mines. But every advantage has a price. In this case, we pay it with bridges that last 30 instead of 100 years. With buildings that need major rehabilitation twice as early as intended. With the roughly $276 billion the United States spends each year fighting corrosion. Maybe that is an acceptable price. Maybe the ecological benefits of recycling outweigh the costs of more frequent repairs. There is no simple answer. But there is another question. The question of honesty. When a bridge designer assumes a service life of 75 years, does she know that the rebar actually used, under real conditions, may hold only about 30 years? When someone buys an apartment in a coastal high-rise and signs a 30-year mortgage, does that person suspect that the reinforced concrete of the building may age faster than the loan is paid off? ASECE has calculated that bringing U.S. infrastructure into an adequate condition would require, over 10 years, about $9.1 trillion. Current committed funds cover only about $5.4 trillion. A gap of roughly $3.7 trillion remains. These are not just abstract columns of numbers. Behind them are bridges that collapse, water pipes that burst, buildings that crack. A significant part of this crisis is the result of decades of building with materials whose real service life did not match expectations. Is there a way out? Technically, yes. Glass fiber reinforcement, stainless steels, new composites, protective coatings, all of this already exists. Bridges can be built for 100 years instead of 30. Economically, it is harder. As long as contracts go to the lowest bidder, as long as owners look mainly at upfront costs, as long as codes do not force life cycle costs into the decision, little will change. Politically, it is even more complicated. Infrastructure means long-term investment. Political cycles are short. A bridge built today, perhaps with steel that is too cheap, will show damage in 30 years. The decision makers of today will be out of office by then. And still, there are moments that offer hope. The Surfside tragedy forced Florida to tighten high-rise inspection rules. Instead of after 40 years, many buildings are now thoroughly inspected after 20 years. That does not stop corrosion, but it creates the chance to detect it earlier. The major U.S. infrastructure package of 2021 provides more than $40 billion for bridges alone. Measured against real need, it is not much, but it is a start. New materials and processes are slowly reaching practice. The first bridges with GFRP reinforcement are already carrying traffic. The first heats of stainless-coated rebar are embedded in real structures. Maybe, in 1 or 2 generations, we will learn to build again the way our ancestors did, not with the same smoking furnaces that once darkened the skies over Pittsburgh, but with a similar result. Structures conceived not in decades, but in centuries. Maybe not. Maybe we remain trapped in the logic of the short horizon. Build cheap, repair often, eventually tear down and rebuild. And maybe every time we cross an old bridge, one built before the war, with a small Bethlehem steel mark on its rivets, we will think for a moment. They knew something we forgot, or they simply had time. Time we no longer have today.